Thank you, everybody. My name is Wouter van der Weengaard, and in this talk, I will talk about robotic matter. And with that, we mean matter of which the shape and the material properties can be programmed at will. You may remember Barbapapas from your childhood time, the cartoon figures that can shape change into any shape they wanted to. Or you have seen maybe the movie Big Hero 6, where robotic matter was fabricated from small cells to fabricate any shape at any time and a reprogrammable shape. So that's what we're going to try to make in our lab. Why we do that? Well, first of all, having robotic matter, you'll be able to do things that you cannot do today. Such matter would also be ultimately sustainable and economical, because in theory, you only need one big box of this kind of matter. And in the morning, if you need a new jacket, you program a jacket out of the matter for you. You need a bicycle, you program the bicycle out of it. And when you, in the evening, want to go to bed, you turn the matter into your bed where you can sleep. It's, of course, a future dream, but it gives you an idea about the far-reaching consequences that such materials could have. Our approach in making this type of matter is to follow nature, biomimicry. So we see that all we living things, like for example, we living human beings, we are built out of 40 trillion small cells, biologic cells, and these cells build up our tissues, and our tissues build up our ourselves as organism. And so we thought that if nature can do that, it should also be possible to do that synthetically. So we should be able to build small synthetic cells, conglomerate them together into materials, and use these materials to build objects, or standing objects and moving objects. This is how we envision a synthetic cell. It has to be a small cell that is anisotropic, mechanically and mechanically. That means that if you rotate it, for example, it's very stiff in one direction and very squeezy in the other. So rotating the cell will determine how its mechanical and magnetic properties are in its surrounding. Cell walls are adapted so they can bond and unbond reversibly from each other to form objects, solid objects, and to loosen so you can reconfigure the objects. And the cells also have to be able to swell and shrink. So if we have one of these cells, as you can see here on the left side in the operations, if we put them together, we get kind of a fluidized matter of particles together. If we then bond these, then we get a solid object of fixated matter. If we then locally part of the object unbond, then partly we get this fluidized matter inside the material. And there, if we turn the cells in a certain direction, we can program, by turning the cells, we can program the material properties. And by moving parts of the cells throughout the solid material, we can program the shape of the material. So by translating. So basically, all we need to do is we need to build cells, we need to be able to rotate them, translate them, and bond them. If we can solve these 4 problems, in theory, we can build our robotic matter. Let us look at what we have accomplished so far. Bonding and unbonding of cells we do through thermoreversible bonding. And here we are developing a novel polymer, PNAGA, which has polymer brushes. And at the hot temperature, these brushes get hydrolyzed, and 2 materials do not bond with each other. But in the cold state, there form hydrogen bridges between the polymer brushes. So if we have 2 materials in contact with each other, they should bond with each other. For magnetic programming, magnetic rotation, we have come even further. Here you see on the left side an image of a test material that we built. It's a plastic material that contains an array of little cells, and every cell contains a low melting point droplet of paraffin or PCl. PCl is polycaprolactone. And inside every cell there's one micromagnet, a small anisotropic ferromagnetic particle. So if we heat this material, the paraffin melts and the magnets can rotate freely. In the cold state, the paraffin is solid and the magnets are fixated exactly where they are. Now we can see that we can program this type of material. For example, if we take a material and heat it up and put it in a magnetic field, you see that on the top left, then all the magnetic particles will align to the magnetic field, external magnetic field. And we see that this material actually behaves super paramagnetically. If we cool down all this material, we freeze the magnetic particles in the solid paraffin, and so we get a permanent ferromagnet. Now we can melt again, for example, and then take away the external magnetic field. And then we see that all the magnets, they will flip down to form what we call an artificial spin ice. So all the particles see each other magnetic field, and they will flip down to minimize their the total magnetic energy. And so this is a form of an unmagnetized state. And if we cool that down, this state is again fixated in a spin glass material. So we have 4 different states that we can program from. Let's have a look how this looks like. For example, going from a magnetized material, as you see here, to an artificial spin ice by simply heating the material. You see when you heat it, you see it melts, and all the magnets that are standing up now fall down, and magnets try to minimize the magnetic field. Another example is when we try to go from the spin glass to the super paramagnetic state in an external field. So here again, we melt, and we see that all the particles that are laying down now go and stand up and form a permanent magnet. The relevance of this type of material is that we now have a plastic material that is ferromagnetic with a high remanence, and that we can reprogram at will with only heating up a little bit. So it has an effective Curie temperature, that is the melting temperature of paraffin, which is about 50 degrees. So we have a material that does a polymer magnet that you do not need to degrade to reprogram the magnetic field in it. Just heat it up to 50 degrees, you can reprogram it, and it will keep its new state then. We did some studies in looking what happens exactly in this spin ice state when the little magnets fall down. And first we thought they would fall down in a random pattern, but they do not really. Here we see that we get emergence of magnetic vortices. You can see that in this simulation here very clearly. So we see the magnets standing up and how they fall down. And what happens if they relax spontaneously, you see they go to a state where you get magnetic vortices, clockwise and counterclockwise vortices. And now the external magnetic field of this material, we thought first everything will fall down, the magnetic fields will cancel out each other. We find that is not the case. As a matter of fact, we find that these magnetic vortices have a very strong influence on the external magnetic field. And we did a theoretical study of that, and actually we can see that where vortices touch each other, like for example here in these round spots, there the magnetic field is coupled out of the material. So these vortices, the magnetic field lines are squeezed together, and then they have to leave the material to the outside, and that's where you get a high magnetic field on the outside. And this is what you can see. The magnetic field on the outside is high exactly where these vortices collide with each other. And we could further show that there's a strong actually that we can program the remaining magnetic field of such a material based on how many vortices there are. We have also shown that you can use this type of materials for programming specific functions, for example, latching magnets. Here there's a little video showing how that is done. So we put a magnetic material on top of a set of pre-positioned magnets, and then we heat it up. And then all the magnets will follow the magnetic field lines of the magnet. And this is how it looks like in reality. So now we see we place it, we heat it up, the paraffin melts, and all the magnets are actually now turning. This is hard to see. You see only a few of them because you cannot see through, but when we will flip the magnet, you can see how they have all, you can see. When you turn around this magnet, you can see how all the particles are now aligned in a very specific pattern, following the magnetic field lines to which they were exposed. And now the interestingest part is, of course, if you take two of these materials, they will prefer a specific alignment to each other. They will latch to each other. And here you can see that one of these materials, and we'll take another one, an exact copy of it, and put it on top. These materials will tend to latch at 90 degrees intervals. They always jump together in the same way. If you push a bit further, you will force it to jump 90 degrees. There. So easily programmable magnetic polymers. This work has now been accepted for publication in microcrystalline and nanoengineering and should be available online within weeks, I believe. Last but not least, shape change. Shape change we have not published yet, but I can show that we can do it. On this is what you see here. The blue material is a 5mm disc and roughly 0.5 millimeter thick. And here we can see how we change the shape of the shape from a ball, from a circle shape to a T. And this we do by repeated translation of material to the object. It is very important that I highlight for you, I'm going to show this again, that the blue object you see here is at any time is a solid object, and only internally a small fraction of the object is molten or fluidized while we do the shape change. Yeah? So this is only the internal. We have the material pumps itself from one side to the other to go from one shape to another. We use DPINet programming to predict the shape, and here you can see, for example, how this DPINet can predict the shape of the actual pumping of the material very well. And it actually can predict the emergence of flow and the emergence of surface energy. We show that's a very interesting way of modeling this type of material. This work is in preparation for a manuscript, and it will be published with the title Transfiguring Solid Objects by Internal Phase Change Pumping. So can we make programmable matter? Yes, I think we'll be able to do that. There are specific limitations though. The first one is the energy of operation. To do this kind of phase change or reprogramming will take a lot of energy. So it will be an energy consuming material. Also, the operation will go rather slow. To make these shape changes takes quite a considerable amount of time. The resolution is limited by the resolution of the cells, so you'll not be able to make nano scale features such as electronics. So you'll have to stay on the scale above the cells. And the mechanical properties will be limited. They will be typically plastic-like, so the materials may not be suitable for harsh environments. When will it work? Hopefully soon. We have to bring this technology together now. Our limit today is not in what we can do. Our limit today is how much resources we have. We have resources for 3 persons to work on this, but the challenges are really huge. So if you have funding, please do not hesitate to contact me. We can speed up this work and do really great stuff if we have the resources for this. This is the team. We are 3 PIs. Myself, I'm professor in micro and nano systems. Professor Danica Kagic is professor in robotics, and Professor Ulrika Edlund is professor in polymer engineering. And we have 6 PhD and master students that have worked in this project: Kerem, Claudia, Emre, Gustav, Alexandra, and Nicola. And with this, I would like to thank you for your attention.